Alright, we're going to go over the example problems for conservation of energy. These match the problems in the student notes as well as the PowerPoint if you're following along there. Before we do the problems, just a quick reminder on the law of conservation of energy. We're talking about changes in energy within a system. So in our equation, we see that with a before side where we have initial kinetic and or potential energy, and an after side, so that's after the change has been made, what's happened to the kinetic and potential energies. Overall, according to the law of conservation of energy, no total change should occur. When you do problems for conservation of energy, you need to make a special note of what type of energy the object has at the beginning and what type it's got at the end. Often you will not need to use this whole equation, and we'll see that in an example here. Okay, so in example 1, we have a 4.5 kilogram box lifted to a height of 2 meters. So let's go ahead and write in initial height 2 meters. If it were dropped, how much KE would it have as it hits the ground? So since it was dropped, we know that also means initial velocity is 0. And then we can assume that it has some speed as it hits the ground here. And the height at the bottom is 0. Okay, so let's think through what kind of energies are present. If we have a height, then that means we have an GPE initial. We do not have any speed, and so there is no KE initial. Moving to the bottom, there is 0 height, and so we're going to cross out GPE final, but there is some kind of a speed, and so there will be a final kinetic energy. Okay, so if we go back to our original equation that we had on the prior page, we've got KEI plus GPEI equals KEF plus GPEF. We're going to go ahead and cross out everything that's not present, so we can get rid of KEI and we can get rid of GPEF. So that gives us a significantly simpler equation. GPE is m times g times h, and I'm going to put a little I because this is initial height. KE is 1/2 times m times v, and I'm going to go ahead and say that's a final speed squared. Now I actually am going to back up a little bit and change this out. Instead of writing out KE, if I go back and look at my equation, it actually asks how much KE would it have had, not how much speed or mass did it have. So let's go ahead and just leave this as KE final. Okay, so the mass was given at the beginning of the problem. That was 4.5 kilograms. We're going to assume we're on Earth, so G is 9.8. And then the initial height was 2 meters. And we're going to multiply all that out to get our final KE. So that gives us a KE final of 88.2 joules. And that answers my first example question. Our second example is a little bit more complex. So we've got a little girl swinging here. It tells you that the swing is lifted from its original position and then released. It's moving with a velocity of 2.9 meters per second as it passes through the lowest point of its motion. We can see the lowest point is going to be down here at the bottom. And we've got we can call that final velocity. Okay, and we're also going to call that final height of 0 because that's our lowest point. We're going to also assume that this is our highest point here, and so we have some initial height. And think about a swing. When you're pushing someone on a swing or pulling them up, you're hanging on to that swing before you let go. So initial speed is going to be 0. Okay, so we're going to do what we did last time. We're going to figure out what types of energy are present. So there is definitely some kind of initial GPE because there's an initial height. There is no final GPE though, because the final height is 0. And then we have no kinetic initial because we're holding on to the swing before we let go, but there is definitely a final kinetic. Okay, so when we write out our equation, again, we're just going to use the relevant parts. So we have GPE initial equal to KE final. Okay, if we write out each of those parts, GPE is mgh initial, KE is 1/2 mvf squared. Before I solve it, I actually can cancel one more thing. So we're talking about the same little girl on both sides of the equation. They didn't give us the mass. However, we actually can cancel it out because it would be the same thing on both sides. It would divide itself out anyway. So we have an even simpler equation here. We just have G times HI equals 1/2 times VF squared. Make sure that when you cancel the mass, you're only canceling that and nothing else. Okay, so let's go ahead and plug in our numbers. We have 9.8 for G times an unknown height. I'm skipping units here just because I'm going to run out of space. And then I have 1/2 times 2.9 meters per second, and I need to square that. So first step would be to square that 2.9. So 9.8 times HI equals 1/2 times 8.41. And then I'm going to multiply that by 1/2. And that gives me 9.8 times HI equal to 4.205. My next step will be to divide both sides by 9.8. And that gives me an initial height of 0.43 meters approximately. I'm rounding that by quite a bit. On your sheet, you may be able to see that it asks a second question here. The second question is, does the speed depend on the mass of the swing? The answer is no. And the reason is that because the mass was the same on both sides of the equation. If you go back and look up here at our equation, same little girl on both sides, that mass would have been the same and it would divide out. So the mass does not matter for determining the speed or the height.